process, like yes. She's going to be. I will move here and here. Let's get rid of the stuff here. I think computer screws my slides. There's usually something written up here. No, se puoi cliccare sulla parte di sinistra della finestra dove ci sono. You just drag it to the side. Yeah. Probabilmente si muove solo quello della sinistra. Yeah, okay, just get it out of the way as much as you can. You want down in the bottom part. On the left. Let's not worry about it. It's something. Just then. I think it just goes. Ah, okay. So no, you can just move horizontally. All right. It should not happen. So, okay, so go back to the first slide again. Okay, now they killed this thing here. Nothing moves. Now let's see. Yeah. Okay, so done with all the pleasantries. So what I'm going to talk about today is to give you an idea of how much actually gets deposited and how we can actually physically see how it gets deposited, and then because of that get a much better idea of how to appreciate the rock record. Okay. So mudstones are important because it's most of the rock record, even on Mars, and about 90% of the geologic time is basically in muds. That's just the way it is. And as you all know, most people study the carbonates and sandstones, and that means they get maybe 20 or 30% of what's there, and the rest of it is simply neglected. That's the way it is. They're important as, of course, for hydrocarbons. I'm a very bad person. I'm a petroleum geologist, actually. We're going to suck oil and gas out of those rocks, and today this is not very fashionable. It's very bad. It should be, actually, because I was behind getting some of this stuff actually happening, that they're not getting gas out of shears and so forth in the beginning. But aside of that, they're very heterogeneous and not homogeneous stuff. And so I have a thin section this big. I may have 5, 6, 7 different stones in there. It's just the norm. Okay. And records, of course, a lot of different things in a very short span. The nice thing about mudstones is, even though they're heterogeneous and all of this, we can predict their property and their distribution through studying the sedimentology and sequence stratigraphy in the context of a basin setting. And if we do this right, we also need to have the physical parameters of sedimentation, which is why we do experiments. Because once we have the physical parameters of when things get deposited and how much and at what rate, can predict where the mud ends up in a basin if you assume a certain film regime. And that's what we petroleum geologists do. We find a rock we like, and then we like to find more of it. So that you need to be able to predict things. So I have studied a few mudstones, and sometimes I meet people that have studied 2 or 3 mudstones and they think they know everything. In reality, they have been spared lots of disappointment, because the one thing I learned in 40 years is that each mudstone unit is different. You have to constantly reinvent yourself and learn new things to understand that new mudstone. Maybe if I had studied 10 times more mudstones, I would see some more repeats. But for most of us, even in a lifetime, we never get the chance to see too many repeats, because mudstones are very, very diverse, compositionally and texturally. I got into mudstones by looking at rocks in the Belt Basin, which is Montana and Canada in the US. And I did not do this because I enjoy mudstones. Nobody does. Okay? Those were the rocks I had to work with. There was nothing else. Okay, just lots of mudstones, and you can either say, okay, they're all the same, and you go home and you write a little paper that you call dissertation, and nobody will ever read it. Or you put your mind to it and say, oh, look at that. There are so many different types. And if you're careful, you can actually arrange them in a slice, in a time slice across a basin, and then things suddenly make sense. These things are not random happenstances, they interrelate. You have basically developed a deeper system. So that did this in the 80s. In the 90s, we kept working on this and went up in the strat column. This was Precambrian, and then now it's a Phanerozoic. It's a little bit more difficult, but different because it's biodegraded usually. But even in biodegraded rocks, you can still map out lots of different phases and come up with a fairly sound depositional model in mudstones. And after having done this for more than 10 years, I also realized one thing is that there are lots of sedimentary features in mudstones. They're not just gray stuff. There's lots of sedimentary features, but you don't know what's in it. You can guess, but nobody has to test this. That's why we started doing experimental work, because we want to know how things work, and we want to know why do these rocks look the way they do. What are the physical reasons, the physical history of those rocks that makes them look the way they do? Once we understand that, then we have made substantial progress. And so we did a lot of experiments that relate to the rock record, which is nice. But the next step after that is basically, okay, we can make these sediments do certain things. Now let's try to measure how fast they do it, what variables makes them do it more or less. Because once we have that, and we go beyond what we see, and we can measure, and we can also predict. That's ultimately any science, basically, that studies nature wants to come to an understanding of nature that it allows us to predict what comes next. Everything else is stem connected. Once you can predict, then you have to make the next leap. And so some of our typical experiments I just illustrate here. For example, we take, in this case, we take kaolinite, put it in a flume, stir it up, and then let the flume stepwise slow down. And you can see that, for example, here we get a little bit sediment loss. It goes down, but nothing dramatic. We basically step down by about 30 centimeters, 25 centimeters per second, and then suddenly stuff happens. And these different colors here actually are different salinities: full salinity, fresh water, and intermediate salinity. And you notice that regardless of salinity, when you hit this threshold here at 25 centimeters per second, stuff starts getting deposited. Stuff turns into globules that are shear stress resistant and can be deposited. And then you step the velocity even more, and then simply accelerates the effect. But so what's the interesting thing is that regardless of salinity, it always happens in the same spot. How many of you have the habit of looking in old textbooks when you want to know something? Yeah, that's where the truth is, right? In the textbook. If you looked, clays do not flocculate and deposit in fresh water. Not allowed. Does it anyway? Okay. Salt water, even more so. But the thing is, there's no salinity dependence. You can do the same experiment by changing the amount of sediment that's in suspension. And no matter how much you use, you get basically the same kind of step-down curves. This is fresh water, similar curve for 2% salinity, 3.5% salinity. You notice that regardless of how much sediment you put, the positional characteristics don't change. That's another thing that's typically being put in the textbook, and to increase the amount of suspended sediment starts depositing earlier. And have tested that left and right, I suppose. And so there's a lot of interesting things in textbooks. You work fast. That's it. Okay. And so here the critical velocity of sedimentation is one variable we look for, and each mineral has its own characteristic type. It depends on the structure of the charge distribution on the mineral grain and how fine the grains are. And we can do these kind of curves for any mineral you care for, because interestingly, not only clays flocculate. Would you think that quartz can flocculate? Yes or no?
Yes. Say no, we would still.
Yeah. You would say no, but you're wrong.
I know.
It's fine.
I knew that.
It's fine enough. You're flocculate. Pictures have movies of it. Aragonite, I'm saying, you're flocculate. If you are collecting toenail clippings and fingernail clippings, you get maybe a kilo together, grind it up into a fine powder, that will flocculate. Doesn't matter. Flocculate, which is nice because you like to have much flocculate, because otherwise the seas would be full of it and everything would be dead. No light penetration, right? The really interesting thing is about all these experiments is that there's this red line here, and you can see that if we look at what travels over the bottom of the flume, it's usually silt grains. Coarse silt, because any sediment that you grind, any material that you grind out in the mill or something like this has a certain amount of silt-sized particles. So a lot of it's finer than that, there's always silt, and that definitely always travels over the bottom of the flume. But once we go below this magical marker here, critical velocity, grain size increases, and that's the flocculation effect. And funny thing is, where we observe it, at the bottom of the flow. It shouldn't even happen. The floccules are basically loosely connected bits and pieces. Just a little bit electrical force. And yet, and so at the bottom of any turbulent flow, the highest shear stress is right here. The floccules inside the flow are fairly small, tens of microns. The floccules in the basal Schieber layer, or it's a viscous sublayer, are tendrils with hundreds of microns. Makes no sense if you are thinking of these things in a traditional way, but it happens. So this is something that we are at the moment just studying. Is and visualizing it is a tricky part, because normally muddy flows are so murky you don't see anything. But here we basically, look at this baby here. Sort of moving along, and if we had the right backlighting transition, you could see that this little thing, this floccule is made out of smaller floccules. The ones that are floating around in the flow, tens of microns. It's almost a small fry that's sitting here now. And we start to create like a snowball that you run through loose snow. And so assemble at the bottom, even so they should be. And that's a fundamental thing about when you study mudstones. What I learned is that whenever you think you've got something figured out, next experiment shows you that. But the important thing is we can make experiments. And so we have basically done a number of experiments where we show that mud can deposit it from currents that are strong enough to move sand in bedrock. So it means that sand can transport along, and mud can transport along in floccules at the same time, in the same flow. normally not considered possible, but it is. We tested it. And so this is sort of a little idea of how a mud bed actually builds up at the bottom of the flume. The ripples move along, and every time a ripple comes along, it leaves a little bit of itself behind, which sticks to the bottom of the flume. And then the next one comes along. And so gradually it builds up. This experiment ran long enough that we built up about this much sediment. And if you then take that sediment and dry it out and look at it, see nothing. But you know it was deposited one increment at a time by a living ripple. Looks perfectly homogeneous because in this particular experiment we use very narrow grain size. That's all we got. But basically, if you have a little bit or more wider grain size distribution, then what we get in the rock record is basically things like that. I just outlined it a little bit, extra lines. But we see basically, remember the sediment is about 80 to 90% water. So you have ripples that are perfectly normal looking, but when they're impacted, like this. And so oftentimes you just see sort of low angle, downlapping lamina, and that's your clue. Ripples might be. Okay. You see in various places, we have enough places in the rock record where we can see that. It works for all sorts of muds, carbonates, and then, of course, all those experiments you just seen, there was essentially pure clay. Very pure stuff. Natural sediments are not that pure, they're mixtures. What happens when you're in a mixture? And we're looking at that here, for example. These are typical shales, black shales and others, with nice horizontal flat silt laminations. Those are the ones that were believed, and there's many, many papers, textbook entries about it. These finely laminated shales mean no water movement, was anoxic, everything was there. In reality, be careful a little bit, and this bothered me long before we get those experiments done. You see these little lenses here, okay, thickening and thinning and so forth. To me, that's that microscopic ripples. And so what we did is then did some experiment to see how we can make this kind of texture. We know that if it's just silt and we let it migrate, we get thin silt veneers left on the flume. If we do clay, we get a thin veneer of clay behind each ripple, migrates. We do it together. Here's a silt ripple. It's coarse silt. And those are the ripples that are made mostly on flocculus. There's one fundamental thing here showing up. We can have a sediment mixture that is coarse silt all the way to finest clay. And it will segregate into coarse silt ripples and ripples that are made out of flocculus, which will move at the same time over the thing. And the way it works is basically like this. If you have a floccule that forms spontaneously in turbulent flow, it may contain larger silt grains, 20, 30, 40 microns or something like this, maybe 60 microns. And then they're surrounded by a very loose matrix of clay minerals and fine particles. And that thing is moving sort of in a fluid. Everything has the same acceleration and everything. But once it starts traveling over the bottom, it bounces around. These things are basically breaking up. They have too much inertia. It breaks the floccule. And then the silt basically drops out, and the lighter stuff keeps moving. And eventually, the coarse silt is segregated out of the floccules. Floccules are getting robbed of the coarse silt, and only fine silt and clays and stuff stays behind. So we have basically simply by transporting primary crudely sorted floccules around, we take the coarse silt out because it doesn't fit floccule structure, and it's bed load transported. And so we get something like this. basically have these ripples, some silt ripples and clay ripples migrating along, and we get alternating layers of clay, silt, not necessarily in regular succession, but fairly random, as random as the ripples that are on the surface moving. If we have low sediment supply, we may get Barkhan ripples, and then we get in one flow direction, in flow direction we get little lenses, and parallel to flow we get continuous layers. And when we have high sediment supply, we get transverse ripples. So this is basically how we can make this kind of stuff. That's how it happens. We have done this in flume experiments multiple times, and it works just fine. Okay. There's two end members out of this, and those are the ones that you see in the rock record over and over and over. So we have basically taken an experiment, and side of the water, we have basically fused rocks. Then, of course, we can go a little bit further and say, okay, pour silt and clay, it gives these typical finely laminated sediments. What about if we add sand? Surely it cannot work, right? Sand grains are such large and dense particles. How can they be deposited at the same time as rock crust? But it's not my fault. That's what they do. If you look at the velocity range at which flocculated clays and muds are stable, it's about from 10 centimeters to 25 centimeters per second. And when you look at sand ripples, or fine sand, got about 17 centimeters per second, or slightly medium sand, it's a little bit higher, but basically they overlap. So you can expect something to come together, and we tested that experimentally, and sure enough, this is mud that is 85% water. And before we did those experiments, I thought, oh, the sand will simply just demolish those mud layers simply by traveling over it. It will just have a little bit circulation, turbulence, it will just eat those things. It doesn't. It just keeps migrating straight across this mud layer, and the two don't care one bit about it. And what's that? And then we tested a little bit more, and we basically we sort of set it up so that we get a decrease of shear stress, and we have basically the down the flume, and we feed in sand, and the sand migrates all the way along and forms layers that are alternately with clay layers and so forth. It's pretty much the same thing as we had for the silt clay populations, just recycling. So we can basically get something like this, for example. This is a natural mudstone with sandy layers and lenses in it. No evidence that there's any erosion going on. And this is basically its flume equivalent. Now we can finally, I mean, in the old days, I would have said, oh, in order to get this sand in here, probably there's surface layer that's really water with sharper. Erode it, and then once got into dense enough mud, the sand could be deposited. Now I have said goodbye to that idea and said, okay, you can even do this if you don't change the flow velocity at all, and the muds do not have to be eroded as the sand comes in. So again, we have done experiments to get a better understanding of what actual rock texture means to us. And those these experiments just sort of tells you what is the tip of the iceberg. There's much more to be done and much more to be seen. When we look at, for example, erosion can, of course, just take away stuff, or it can, for example, create new particles. You have a mud is cohesive, we erode it, instead of just simply dispersing it, but little lumpy particles that are mud aggregates. You get new particles, you get new bed forms. You can look at complex current regimes, waves, tides, and so forth. And we have those in the rock record. We can model them in flumes. And then the other thing that you have to grapple with is the role of organic matter, which is a little bit challenging to do in a flume setting, but we're making some progress here. This is the latest design of our flumes. We have 4 of them, but this is Mark IV. And this flume is designed to do all sorts of wonderful things. Like, first of all, it can push shear stresses of up to 2 Pascal. 2 Pascal in this flume means sand grains are flying horizontal. And so we have the power, and you need power to experiment with mass. So they are quite reluctant to be loaded. And so we built a system that, I mean, we designed physically and electronically a flume that can be programmed to do certain things, do certain flow regimes and everything. And here, for example, we're trying to rip apart a mud bed. It's about 85% water. And it's not very exciting. Eat a little bit here, eat a little bit there, okay? And then suddenly out of nowhere, boom. Okay. What happens here is basically what is a rock record what we call a scour. And you see that instead of simply dispersing, chunks of this mud are simply ripped up and are transported away. Okay. And so we basically simulate here something that's probably quite common on the seafloor during storms and something like this. And the next step is then to say, okay, how does this look like in the rock record? You know, this happened at 40 centimeters per second, and that is basically about half a Pascal of shear stress. Other muds we test, they make more shear stress to be eroded. This is a relatively low-end mud, but in any case, muds that consist of compacted soft fishing lumps are common as well. This is an example here from the Cambrian of India, but we have them from all ages basically. I call this lenticular fabric, and basically little lenses, stand size and larger, of mud aggregates that must have been soft before being compressed. And we basically experiment this all the way through. We eroded this a mud bed. We transported the little lumps along, and then at the end we deposited them, and then we pretended to water out there, just vertically squishes that stuff in Photoshop, and then we get this kind of fabric. So we know how this happens. It is common, very common. In the rock record, a nice example is here from Romania, the so-called bituminous malformation, which is all you can see. This is the source rock of the Romanian oil fields. And this is what it looks like. Sort of nice, evenly bedded. There's some sand layers in it, ripples. It's basically, for lack of a better word, probably a deep water controlite. It's relatively far offshore. It's a toe off the slope and stuff like this. So this is basically mud and sandy layers intermingled. Could ask, how do we do this? We have the sandy layer I can understand, bottom currents, transport and so forth. Easy. But what about these guys here? What happened here? Because you have, I mean, every layer that is visible clearly shows as a current going. Did you turn off the current in between? Well, first of all, if you know that there's a lot of water in this stuff, about 75% volume percent, as in outflow, probably a little bit more in reality because these plastic dikes did not come on day one, they came a little bit later. But if you look at the rock, as a regular syntax, you see that it actually consists of a lot of sand-sized flattened particles. With this stuff here, it looks like a mudstone. Everybody calls it a mudstone. But before it became a mudstone, it was a sandstone. It was just the wrong kind of grains. It was grains that in themselves fine-grained aggregates. So you squish it back together, so you only fine grains. So a lot of mudstones in the rock record, when they were deposited, were quite a bit more coarse-grained and different. And when you have these recycled mud, and to be a little bit more cohesive, the initial flow from exchange. It should have an aggregate that's a little bit more rural. It acts like a sand grain, and sand grains, when there's another group, make ripples. And here we basically have, this is a coin here, but this is about 5 centimeters or something like this here. You see the cross beds very clear. The cross beds internally look like this. Okay. So we have cross-bedded mudstone, which means, no, we didn't have a mudstone here, that's physical mud aggregates primarily. In between, once in a while, there's enough sand around to do this, but most of the time we don't. So here, because this stuff was about 75% water at least, before they got preserved like this, they were about this tall. On the modern seafloor, they would be called megaripples. So look. The individual thin layers here, those are probably made by small ripples, but here we have megaripples. Bed load transport all the way along. And if you want to go a little bit further, well, this is an outcrop. There's a hammer. The master bedding planes are here. And then there's that thing here. So you're looking at basically a mud wave that has been preserved accidentally. That thing might have been several meters tall. So, and because we were in a relatively deep water setting, for the 2 meters mile, we have deep sea environments in other parts of the world which have huge mud waves in them. And this might be just part of the spectrum what we see here. If it were, could be any larger, we wouldn't even notice that it's there. And so we did that kind of experimentation. We're still working on that, but so we have taken laminated shears and tied them to process. We have taken lenticular shears and tied them to process. Okay. And now let's look, and we did the sandy shears and so forth as well. Not all flow is unidirectional, most of the time it's not. And so here, for example, this is just a thin section of a shear, parallel laminated, all accounts. And then what I did basically, I spent a lot of quality time with this thin section and literally traced out each lamina by hand. And then I took Photoshop and did. Looks like this. You can see that there's cross-lamination in it, scouring, truncations, and so forth. This parallel laminated shear is actually this. It records a very different story. In this particular case, it probably reflects wave action. Okay, there seems to be some sort of a bimodal distribution of currents. And here we did a flume experiment here with a tidal program. You can see that we have basically a ripple that first moved this way, and then we reversed the flow and it moved that way. And we have done experiments that ran for several months, building up mud. I would say that we get beautiful ripples. Internal structure that is unlike any curve we ever saw in the case that it was proposed. So we can actually take the flume and make imaginary sediments. Then we go back to the rock and we see if we can find them. Yes, we do. So the mudstone rock record contains pretty much everything you see in the sandstone of the Calvary in terms of sedimentary structures and the associated connotations with respect to depositional setting. So here just a little unidirectional curves might get use this kind of few tidal currents may get use this. We have done this. Storm wave reworking, so slightly different. We haven't done that yet. That's experimentally a little bit more tricky. But it's doable. But by basically looking at mudstones and making experiments that produce these kind of textures, we may be at some point able to move to link flow velocities and sedimentation rates to a fabric. And then we really can get into the prediction business as to why a certain muddy succession looks the way it does. Not done yet, but we're working. In more simplistic terms, we have a sort of a phase diagram of depositional features, surface features, in relation to sedimentation rate and flow velocity. And that's sort of where we want to go. We know this is like this. Where the boundaries go exactly, I'm too lazy to do this. I wait for some other people to figure that one out. I would rather lay out this is how it works, and you guys can figure out the details. And so where we're going with this is where most of our experiments happened. But this is what the rock record tells us. This is rock record. I mean, this is experiment we have in the rock record as well. So this one is pretty well covered. We know from looking at real rocks that we have something going on out here and probably even out here. So we have to start working our experiments this way. The only problem is the flumes get larger and larger and larger. And the experiments take longer and longer. So, but anyway, it's I mean, we have this one slice in the data space, and the rest of it is conjecture. But there's reason to think that certain things that we have seen on must be there. Then we have, let's say, I told you earlier that different minerals have different critical velocities and all this kind of stuff. That's not very convenient. Each mineral has a different set point position. Lots of minerals in the system. Trying to predict what's going on is going to be very, very complex. But fortunately, organic matter is taking action that change. Organic matter just sticks. Just sticks to quartz, to go that way, polyethylene or something like that. So we have organic glue in the natural environment that brings these things together in organically supported molecules. And that's probably, in the end, will be the great unifier that makes field sedimentology simpler. Certain velocities are like about 25 centimeters, where things simply things basically become bed load floccules and also stuff that we have seen already happens. This is just another one of those experiments with mostly organic matter. You can see that you have wave after wave of organic floccules moving through. And now just add a little clay to it, and the floccules get a little bit heavier, and then the behavior of that whole system changes. But even when it's all organic, you still have backload that forms. Never is start raining out of the water column, and then it's there. Even if it comes down this way, as you see before, Most sea floors have currents flow, and actually not too slow. The reason why you can still build up mud on those sea floors is because of the starting temperature. So flume studies can replicate rock record fabrics, okay, like lenticular fabric, laminated fabric, and they have done so rather nicely. We have been able to do this and made a fairly convincing case that our experiments indeed replicate common sedimentary fabrics of mudstone. And then we can say, okay, these are the boundary conditions under which this happens. Now, we have sort of, I mean, essentially we have sort of looked at 3 different families of fabrics to do this. In reality, it has a lot of different mudstone fabrics. I'm going to just give you a few examples to keep it interesting. Okay. And I have in my lab how many thousands of sections. I would go through there and check out all the different fabrics on a big blackboard or something like this. There would be hundreds of fabrics for sure, dozens of fabric families, and these 3 main fabrics that we have looked at: laminated, silt clay, and sand laminated, and lenticular. That has taken us 15 years. That covers a pretty big chunk of the mudstone realm, but there's more to do, basically. And so there's a couple of decades of work left, for sure, because there's no other lab on this planet that does this kind of stuff. There's the only lab in the solar systems that does mudstone experiments. I mean, the Dutch and some of the engineering people have done experiments with mud. But the interesting thing is they never looked at what they're getting. I had a very interesting conversation early on with a civil engineer. There's something wrong with we know from our experiments that much erosion threshold at about, I mean, place, they don't currently place. I have an erosion threshold at about 25 centimeters per second. You say it's 15 centimeters per second. There's something wrong with you. No. Me, I'm just a geologist. I don't know maths of this kind of stuff, right? How are we going to have scale access? How did you do your experiment? Oh, we have these big angular flumes, and we put stuff in there, and we let it rotate, we get beautiful shear stress measurements. We know exactly what's going on. Actually, I would look at happening while we're rotating the flume. We measure the suspended sediment, then we know what's happening. The only problem is the flume channel is steep. Puts a sensor right here at the half height. When you erode a mud bed, the first thing you generate is little lumps that travel over the bottom of the bed. They don't even make it up to here. So if they had looked, they would have seen all those little mud balls migrating around in circles, and their bed being eroded, but because it didn't register on their suspended sediment sensor. That's a fundamental logical perspective, shortcoming of engineering studies, because they want to have something that's easy to measure, and they do not look at what happens when they do it at the bed. They don't want to look what's accumulated afterwards. And if you do that, it's a simple world. And so there's I mean, when I started this, I thought, oh, yeah, the engineers have been doing all these kind of experiments for a decade or two. I should try to get that information and find shortcuts for my own research. too fast. And then I finally realized that it does not make any sense. He said, I'm stupid or what? And so we did experiments again from scratch. And we realized that it works different. And that's, it's probably not in sedimentology or not so that it's the only place where this happens. It happens more commonly in science, I think. But anyway, so what is it all good for? Once we understand shale fabrics, how they form, under what conditions, then we can take the 70% of mudstones that are in the rock record and milk them for information about depositional parameters, what flow velocities, what rates of sedimentation, and all that kind of stuff. And then we can loop back to the global condition and the environments of the past. We can get a lot of information about what the world looked like out of these sediments. Instead of getting it from the interbedded sandstone units, we get it from the whole thing. And that will, of course, help the people that do climate studies, if they want to help. Perhaps they don't. And of course, your hydrocarbon recovery is a good thing too, because I'm willing to make today everybody is going to save the planet by buying an electric car and stuff like this. Not knowing where the electricity is. I'm making the bet with you. But you're young, you're going to be around for a while. That 20 years from now, 30 years from now, we're still using a lot of fossil fuels. Not hydrocarbons, not necessarily for burning them in the car engines and stuff like this, but for making plastics and also other things. Can you think of like some sheets and stuff like this, which is a very nice, wonderful material. It's extremely durable. Can shoot a bullet at it, it doesn't go through. Very much tougher than real glass. It's made. And so there's a lot of things that we actually need to even build fancy high-tech electric vehicles. It's made out of bloody plastics that comes from oil. Cannot live without it. But that's the way it is. It's relatively easy for people to get excited enough to glue themselves to a painting with super glue and think they made a contribution to progress. Or you can think about what's really happening and change the world. Anyway, so when we talk about experimental study of mudstone sedimentology, this all starts at very tiny building blocks, but there are lots of interesting prospects out there of where this can lead us with respect to understanding total volume of sediments in the sedimentary basin. Lots of work to be done still, at the beginning really, but no matter what experiments we do, there's always something new to learn. This is one thing, we have been experimenting for 15 years. Sometimes we have done experiments that went horribly wrong. Absolutely unexpected. Sometimes you get into, oh yeah, we understand this now, let's do this experiment and fill out space. And then something happens. But then, of course, you learn something new. Realize we didn't understand the system and concepts. So even though we have lots of flawed experiments, none of them every experiment was worth the sense that we learned something. Never had experiment that was so boring that why are we still doing it? Yeah, not even close to that point. So anyway, thank you for your attention, and just for the fun of it, I like to be right here. Typical academics that like to go home at 5 o'clock or 4 o'clock on Friday, they like to be here. There's also lots of good work to be done here, but the cool stuff is happening over here. You might embarrass yourself sometimes. But on the other hand, you can also find really cool stuff. All right, that's it.
Thank you. This is really useful and interesting presentation. Yes, it's time for the question. The question is here, and we can